Okay.
Hello, everybody, and welcome. I'm very happy to see such overcrowded room. It's all about Jan Vysoký today, because it's our kind guest who has been invited plus or minus a year ago and made another beautiful talk. So it's my pleasure to introduce his today's talk. It's graded geometry, and as you can properly see, I hope this is supposed to be the first part with approximately two-part kind of talk.
Approximately, yes.
Approximately, and I would like to announce that today it is going to be obviously the first part, and
it will be really fun if I will start with
and the second one will take place not next week, but the week after, because of some internal.
That will be public told by 3 days.
Yes.
Not 20 in K1, so you are invited to go listen to that one.
Yes. So, as to finish my part, I think you might know Jan is a researcher at the Czech Technical University. He came from the Faculty of Nuclear Sciences and Physical Engineering. So this is my full stop.
Okay, so thank you very much for the introduction. Thanks everyone for coming. And I hope I will tell you something interesting. So this is a work in progress about my attempts to construct jet manifolds and more generally jet vector bundles out of graded manifolds or graded vector bundles. What I mean by graded, throughout the talk, graded always means z-graded. But most of it probably applies also for supermanifolds, so this should also work for supermanifolds. And I will roughly divide my talk into three parts. First, two of them, or 1.5 of them, should be presented today. So first of all, my starting input from this construction is always a graded vector bundle. So I start with a graded vector bundle and then construct jet bundle out of it. So, not only jet bundle. So I have to explain you first what I mean by graded vector bundle. So first part will be about what is a graded vector bundle. The second part will explain differential operators on these vector bundles. So linear differential operators. So differential operators on sections of those graded vector bundles. And the third part should be kind of the pinnacle. It will tell you about graded jet bundles. Graded jet bundles. Not pinnacle, but part of the thing. This is also interesting. So this is the plan of my talk. And of course, graded manifolds are then obtained. Jet manifolds are obtained as a special case by considering trivial vector bundle with fiber just R. Okay. So this is my outline. So I will hide it so you don't see it. Okay. So first of all, so part one. So first of all, graded vector bundles are some structures which require graded manifolds to exist, right? So I have to tell you what is a graded manifold. So, and I will be as vague as possible. So what is a graded manifold for me? So a graded manifold consists roughly of following data. So what is for me graded manifold? So first of all, everything lives on some topological vector space. So I have some, topological space. So M is second countable Hausdorff topological space. So this is first, the most important part of data. And second, I have a sheaf over this topological space. So there is a sheaf, which I denote as C infinity curly C M. So this graded manifold is denoted M. So I have a sheaf of smooth functions, and this sheaf is sheaf of graded, Z-graded, commutative, associative, unital algebras on this topological space M, on M. There is no space here. Okay. So what I have, so for each open subset, by this sheaf I mean that for each, I have some algebra of all these four properties. So I have some Z-graded, graded commutative, associative algebra with a unit. So, and this is of course called algebra of functions on this graded manifold over this open subset, let's say, right? And I don't want to go too much into detail, but what I mean that it's a sheaf, this means that I can, because it's an algebra, I can linearly combine functions, I can multiply functions, and because it's a sheaf, I can restrict functions to smaller open subsets. And because it's not only pre-sheaf, but it's a sheaf, I can glue functions which are locally defined and agree on the overlaps to global functions. Roughly, right? So this is the second part of the data. And then there is third part, which I will state even more vaguely, that locally it has to look like something, right? So there is some model, there is some rho model for graded manifolds. So around each point M of this topological space, there is some pair which is called local graded chart. And this U is this open subset around M, and this phi is some map going somewhere. It's some map of morphism of local ring spaces, blah blah blah, but it's not really important. What I wanted to say that it induces some local coordinate functions and some of them are of degree 0. So these are elements of this algebra of degree 0. And I also have some functions which do not have degree 0, of not degree 0, not 0 degree. And these coordinates somehow commute. It's not really important at this moment. What is important is each function such that each function on this open subset, so element of algebra over this U, looks, and how is the exact word? Can be described. Can be described as uniquely as some formal power series in this coordinate, as formal power series. I don't want to write here equal because it's not strictly true, but we can basically describe it as some power series, and I want to be as vague as possible. So there are some coefficient functions which are functions of these degree 0 coordinates. They are smooth, and then there are some polynomials in these non-zero degree coordinates, and they are not really polynomials. You have to consider formal power series, so you in principle have to consider infinite formal power series for it to make work. So this is what is graded manifold for me, very vaguely, because I don't really need to work with these local expressions too much. Sometimes yes, but not too much. What is most important for me is this algebraic part of the data. This sheaf has to satisfy something. It has to be some local limit space, graded local limit space of graded commutative associative algebras. One notation I will use is that both of these coordinates together I denote as single collection of local coordinates when this n is sum n0 plus n star. So I have some finite number of degree 0 coordinates, some finite number of non-degree 0 coordinates, and I combine them together into a single collection of functions. So there are some easy commentaries.
What are morphisms of these things, or coordinate changes? Are you allowing that?
Basically, you can describe them as by pullback of this coordinate function. So you can, every morphism is uniquely described. You simply say what is a pullback of coordinate function and express it as some form of power series.
But for example, if I have two graded manifolds, am I allowed, and I have one graded manifold something from 0 in the 1 degree component and minus 1 degree component. Is the product of it allowed to go to a 0 component and that?
Yes.
Okay, it could be.
Yeah, you can mix. It's not like the simplest example of graded manifolds are usually such that they do not mix non-zero degree coordinates into 0 degree coordinates. But here you can, for example, you can define pullback of like you have some coordinate functions xi, and you define this to be, let's say, some infinite series in this size such that the sum of degrees is 0. You are allowed to do this.
Okay. Sorry, can you walk towards the camera because it's so blurred at the moment? I think we can improve it if you walk and then go back.
Does it? Did it? I was too fast.
Yeah, maybe try again.
I will show some hand gestures.
Maybe a bit closer again, a bit more. Okay.
Yeah, that's true.
And for more trick of magic, so we can continue. Yeah, I didn't improve.
Okay, so there are first there is a notion of graded dimension. So graded dimension of M of this coordinate M is a sequence of non-negative integers nj indexed by integers, and this nj is simply number of degree j coordinates in this setting. So it's really a number of coordinates za such that, or with a, the number of a's such that degree of za is exactly j. So you count the number of your coordinates of given degree, and this you refer to nj, and you collect this. I should write. It's a sequence, right? So you have to remember the whole sequence, and you assume that in this we always assume that sum of this nj is always finite. So you don't allow kind of infinitely many coordinates altogether. So sum of all coordinates j has to be sum of the number of the all coordinates has to be finite. So this is finite, and we call this n total dimension of m. We sometimes index things from 1 to n, for example, those coordinates. And the second observation follows immediately.
What is this cardinality of this set?
This number of indices, cardinality of, this is stupid notation. It's number of, number of.
I understand it, but this is set.
This number.
What is that?
It's simply number of coordinates which have degree, number of those coordinate functions which have degree j. So if n free is 5, it means I have 5 degree free coordinates on my graded manifolds. Maybe this notation is somewhat wrong. I'm not really strong in this formal combinations of symbols. And the second observation is that this topological space M always becomes ordinary manifold. So it's ordinary manifold with local coordinates, and of course this x1 to xn0 then are ordinary coordinates on this ordinary manifold, and there is always a map. There's always a projection. There is a projection, surjective one, in fact, projection which goes from smooth function on graded manifold to ordinary smooth function on this ordinary manifold, and it is usually denoted somehow, and I denoted it as f underline. So, and this is called sometimes body of the function f. And there is always map only in this direction. In general, there is no map going the other way around, globally verified. Okay, so these are graded manifolds for me. And so I can now define what is a graded bundle, graded bundle function. So I will now say it quickly and then describe for 20 minutes what it is. So a graded vector bundle denoted as curly E or curly M, so it's always on some base over M is, and now comes the definition, a locally, freely and finitely, finitely generated sheaf of graded C infinity curly M modules, and that's not it, that's not all, of a constant graded trend. Constant graded trend. And this sheaf, I have it here, but I didn't write it, so I will move this a bit left. This sheaf is denoted as gamma E. So I directly define vector bundle, graded vector bundle, by declaring what is its sheaf of sections. And that's it. And I call this sheaf a graded vector bundle, and kind of to make it look like ordinary geometry, I then call it somewhat differently, but what I really mean all the time, I look at this sheaf.
In the ordinary case, it's projected, right?
There's something different. There's something different because you can say in ordinary geometry, you can say that graded vector bundle, the vector bundle is a projective, finitely generated module, single module over global functions. And there's something different. Here I say that I have full sheaf of sections, so I have local sections over each open subset, and then I just want it to be locally, freely, and finitely generated over constant graded track. And I will now explain. And this is called sheaf of sections of E, of course. Sheaf of sections. So graded vector bundle is something which I call its sheaf of sections. Kind of strange definition, but I like it because it enables with standard differential geometry. Okay. So let me break down this definition now, right? So first of all, for each open subset, so I will write set of open subset as this. So U is element of this open subset M. For each open subset U, this sheaf evaluated on U is a graded sinking MU on U. What does it mean? It means that, okay, so it means that it's a graded vector space. Right? And I have some action of functions acting on this graded vector space. So for each function over U and section, which is an element of gamma EU, there is some section which I denote as F dot psi. Right? And then there are some axioms, such that there are some axioms satisfied by this axiom, so but they are completely the same as for the ungraded case, except of course you kind of assume that this operation is graded. So f times psi has a degree which is the sum of the two degrees of f and psi. And then there are standards like if you, so you can kind of write this rebracketing, and what else? If you act by 1, which is always in your algebra functions because it's unital and it does nothing. And then there is also the fact that this dot is to be R bilinear. So if you add two functions, then you can distribute it with respect to addition and scalar multiplication in your graded vector space here and graded vector space here. Right?
Excuse me.
Mm-hmm.
I have just a question. Sometimes you use M and sometimes you use M calligraphic. I use this.
For example, here is calligraphic.
So
This calligraphic M
yes.
is a notion for my graded manifold, which is defined by its sheaf of function. And this non-calligraphic M is always the underlying topological space. This M is this ordinary topological space, which is always ordinary manifold of some
Okay,
magnitude.
but how many coordinates do we have for M calligraphic and for N?
For M calligraphic, we have N, I think I denoted it as N0. So N0, this number N0 here is the same thing.
Yes.
It's always the dimension of this non-calligraphic M, and then we have nj of degree j coordinates on my calligraphic M.
If I understand correctly, M and M calligraphic, they are not the same topological space.
Calligraphic M is not topological space at all.
Okay.
Calligraphic M is not a topological space. It's just a notation for me having a sheaf of functions over this non-calligraphic M. It's kind of standard notation from super geometry and graded geometry. Because you want this theory to resemble ordinary geometry as much as possible, so you abuse notation all the time just to achieve this, to my understanding.
So what would go wrong if you would only assume the NJs to be finite?
NJs?
Yeah, for each J.
Yeah, some kind of this degree-wise finite dimension or something. Nothing, basically. Almost nothing. There are some things which do not work. The definition does work. The most basic theorems do work. But for example, what does not work is inverse function theorem. Or I'm not saying it doesn't work, but the proof collapses. Because when you prove it, you somehow, for each degree, calculate some open subset where something works. And then you have to take intersections. And if there will be finitely, infinitely many non-zero dimensions, then this intersection couldn't be possibly over empty, something like that, or containing just a single point, something like that. But in principle, it works. But for simplicity and for all practical purposes, for me, this nj, some of them is finite. Right. Okay. Here is the time flies. Here is the work. So, okay, I have a sheaf of, I have a module of local sections, and then what is this locally, freely, and finitely generated constant frame frame? This basically means that I have local frames. Just to state it really quickly, I have local frames. And I will formulate it precisely in this way. So, there is number 2, which I have here. I was not talking about the sheafy stuff. So what I can do, I can restrict sections and glue them together. So that's hidden in the fact that it's a sheaf. So local sections can be restricted, and glued. So if I take smaller open subset, I can always find a map going from gamma EU to gamma EV, respecting all the structures. So it has to be linear with respect to this action, it has to be linear with respect to scale multiplication and addition, and it has to, and that's it, right? And if I have some collection of local sections which agree on the overlaps, then I can glue them together to a section on the bigger open subset. So that's basically what is hidden in the word sheaf. And what is hidden in the word locally, freely, and finally generated means that, well, first of all, there has to exist some fixed graded vector space. There exists a finite dimensional finite graded vector space K, which is called the typical fiber of my graded vector bundle, called typical fiber of E. And I fixed some its global basis, the total basis, with some total basis. What is total basis? it's a basis where I fix a basis in each degree of my graded vector space, and because it's finite dimensional, this total basis is some finite collection of elements of my case. So, so I have some collection labeled from 1 to some finite number r, and each of it has some degree, which is not really important. It just has some degree. It has some degree, and because it's finite dimensional graded vector space, I can always do this thing. And so this is what I have fixed throughout for the whole picture, and then this locally free and finitely generated means that for each point, m of m, there exists some open subset containing n, which I denote as notation should be somewhat clear. This is an open subset containing my point, and some collection which is called local frame. It's called local frame or E over U. So this is just a terminology resembling this classical one, and it's some collection phi lambda. Lambda goes from 1 to r, such that so it's subject to some definition. So first of all, the degrees of those elements. So first of all, phi lambda is a what? It's a local section over U. So each of them has to be a local section, and it has to have the same degree as the corresponding element of the total basis. So somehow I assume that I can always order them in the same way. And this is basically what is hidden in this over constant graded length assumption for all 1 to r. And second, they finitely generate, because there's finite number of them, and they freely generate gamma EU. So for every V subset of U, any section of E over U can be written, running out of space. I will write it here because it's important property. So it can be written as psi. The sum lambda goes from 1 to r at lambda dot lambda restricted to b. For unique, it has to be unique decomposition. For unique functions f lambda living in C infinity curly m u, and their degree has to be, of course, because sum of degree of this guy and this guy has to give degree of psi, so it has to be. In my description, which I didn't want to go into too much, all elements of all graded things are always homogeneous, so they have always well-defined degree. So I have no non-homogeneous elements, but it's not really a matter, because when you work with non-homogeneous things, there are always finite sums of homogeneous things, so it's not really too much a complication. And that's it. That's my definition. So graded vector bundle It's really some sheet which locally is generated by some local frame, so I can always go to local description and work with just some coefficient functions with respect to some local frame.
So is this equivalent or like a bit stronger than like just projective time-generated modules, like a sheet of?
What is interesting, and I think I have a proof that there's a strong claim that GVB, graded vector bundles, is not the same thing as graded projected graded C infinity curly M modules finitely generated. So this means that there is no, this effect is called Serre-Swan theorem. So there is no Serre-Swan theorem. This definition, in fact, what is true is this thing. So the space of global sections of every graded vector bundle with respect to this definition is finitely generated projected graded C-infinite M module, but not the other way around. And I have counterexample, which I won't tell you. But I have it, yeah.
Which property will be evaluated?
Actually, I don't know. The counterexample just tells you that I have found example which is not a graded vector bundle, and it's all of these properties. So I have some generators, and then I prove that what I prove. Somehow it's not compatible with this, right? Because graded vector bundles, it's not clear from these definitions, but graded vector bundles have fibers. Still, they have fibers. You lose a lot of information about your graded vector bundle if you go to fiber. So it's not true that you cannot reconstruct graded vector bundle just looking at the fibers. That's the same as in supergeometry. And these fibers have some properties. For example, local frame. If you can evaluate local frame at each point and you obtain the basis of the fiber. That's true. And somewhat I was able to prove that I have chosen some generators. They define some projected graded C-infinite module, and it turns out that there is no local frame for it. So, or not even local frame. So I found projected modules where you cannot find a local frame for it because it violates some property of fibers, basically. Just to be short, and I believe it also fails it has to fail for the same reason in super geometry, I believe. But maybe it's too strong a claim. For me, maybe my counterexample is wrong. But I firmly believe that, not so firmly, I just believe that it's true. It's not true. So you have to really use this definition. They are not just projected graded modules, finitely generated ones.
So just a quick technical question. So do you consider the zero section should be homogeneous?
No, in fact, I have. That's funny thing in this description I use that all my graded vector spaces it's just a collection of vector spaces in each degree. So I have zero vector in each degree. So I have to specify which degree zero I am talking about. So I have zero sections for each degree I choose. Right? This is kind of strange, but it doesn't. Kind of in practice, it doesn't violate anything. So the answer to this is no. What is the answer? That I have zero section in each degree separately. That's my answer. But I can explain to you later. Maybe I don't want to waste time on these fundamentals because I want to go to differential operators. I should now, right? but I can erase everything. And first I have to talk about something which is kind of the same as for ordinary vector bundles. I will talk about local operators on sections of graded vector bundles. With some class of mappings between spaces of sections which have some nice property. And these are important because you can restrict them to smaller subsets. Okay. Okay, so it's sorry. Before going to this, of course, I should give you some example of graded vector bundle, right? It's probably a good idea. So of course, the obvious example is tangent vector bundle, right? So for each open subset, I define a module of graded derivation of my algebra of functions. This means that element of this thing is a map which goes from functions over U to functions over U, and it satisfies the Leibniz rule. It means that if you act on product of two functions, and there is a sign which is always the Koszul sign, so this map can have some degree, so it can raise the degree of functions by some given integer, and this degree appears here because you have to commute x through f paid by some sign. So this is what the elements of this graded vector space are. So this is obviously a graded vector space, and there is the action of f of functions on this is also kind of the obvious one. I use some bracketing here. So f times vector field acting on G, you first act by x on G and then multiply this resulting function by f. And this is what is this C infinity MU module structure. So this makes it integrated. There is C infinity MU module. To show that this is a sheaf, it's not that easy. It's a kind of common trick, but you have to use partition of unity on your graded manifolds, otherwise you cannot do it. So, but you can use that. You can restrict that. You can uniquely restrict vector field to smaller kind of C infinite and V, when V is a subset of U, and you can uniquely restrict it in some sense. And this gives you this sheaf structure of this sheaf. So these elements of these module are called vector fields, and this is called the sheaf of vector fields of M. And this is the sheaf of vector fields. On this called M. And I claim that this sheaf is locally, freely, and finitely generated of a constant graded rank, and this is why, because you can take some local graded chart for a manifold. So you have some open subset, then you have some set of local coordinates. So basically, you produce a set of local coordinates, and then out of this, you can produce a collection of coordinate vector fields, local vector fields, which act in kind of expected way, except you have to deal with formal power series, so you have to be a bit careful, but it works like it should. And this form a local frame, form a local for some bundle which is denoted as Tn over U, and this sheaf of vector field is then declared to be sheaf of sections of the tangent bundle. So this is a nice example of graded vector bundle. You have to prove that this generates only vectors, but the proof is kind of standard. As for ordinary manifolds, okay. And there are other examples. There are dual graded vector bundles. Dual to this graded vector bundle is called cotangent bundle. You can do all gymnastics with graded vector bundles you want. So you can do sums, you can do tensor products, you can do pullbacks, you can do, I don't know what else. You can produce fibers out of them, etc. You can do, yes. So if you there is a well-defined notion of submanifold of graded manifold. So you can, for example, then you can observe that tangent bundle to this submanifold is a subbundle of pullback of this original bundle using this map, and then you can quotient out and you have normal bundle. So everything works.
So pullback is universal.
Sorry?
The pullback is universal.
Yes. Yes, so this is really the same. The construction of pullback bundle is quite tricky. It takes a lot of work and also the tensor product, because you have to tensor product to sheaves, and then it's not a sheaf, so you have to sheafify something, blah blah blah, and then kind of go through everything and check that this sheafification really doesn't spoil nothing. So it works. And I will now go to local operators. So what is the definition? So definition. So I have some open subset of M, and I have some map which goes from sections over U to local sections over U. And this map is graded R linear. So just for simplicity, I assume that it's linear as a map of vectors, graded vector spaces, and chalk. And one says that F is local. Well, if the situation that some section vanishes on some open subset of U, then this situation has to imply that also the image of psi vanishes on V. So this is what I declare to be local operator. And they form graded vector space because some linear combination of same degree local operators is local. It's easy to check. So they form a graded vector space, which I denote as log E of U. What are examples? What are examples of local operators? So examples of local operators are C infinity M linear operators. So we say that F is C infinity curly M U linear. It's a definition. If F on F times psi is, and there is also this sign here, so degree of F times degree of the function F times F of psi. So this is what you call infinite M linear map. And example says that then F is local. And F is local. How does one show this using bound functions? This is the same trick as in standard geometry. There you want to prove that the map only depends locally on the values of the section. You have to use bound functions to do this. And There is a nice observation. I think it's nice. And this proposition says that this locality ensures that, and maybe I don't know if it's equivalent or not, but definitely it ensures that you can restrict. Local operators can be restricted. So if you take a local and uniquely, so if you take a local operator on U, and you take some open subset of U, then there is unique local operator. It's important to say that it's local because of this uniqueness claim. So there's a unique local operator over V such that it satisfies the expected. So if you first take section of U, restrict it to V and map it, is the same thing as if you first map it and then. And this condition determines it uniquely. So there is no other local operator over V which has this property, which is very useful in some constructions. Okay, and what is also interesting, and this is not so interesting, this is standard, this is not something interesting, but you can prove that it in fact defines a sheaf again. So this log E is a sheaf shaft. Sorry, sheaf. I hesitated for a second that there is ski. No. Agree. I'm starting to be a bit sad. Log is a sheaf of graded C infinite M modules. So the action of functions is obvious, it's the same as for vector fields. So f times local operator is defined to be f times the result of the action of the operator. This gives you action of functions, and you can prove that it's a sheaf. So this is the restriction on your sheaf. This is the restriction on the sheaf, and then you have to prove that it satisfies those. You can glue local sections together, but it's true, and it's kind of, and it's easy, but it uses all the time that this target vector space of your match are sections of the sheaf. So you really need this gamma E is a sheaf. Okay, and then we can start part 2. It's a differential operators. So at least I will tell you the definition of some basic properties, and this is probably where I will have to end. So give me 10 minutes. Fine. Sorry. The definition of differential operators I will give you is also kind of mimicking the standard case, so it's not really too innovative. But the point is it works, it's nice. But it wouldn't, right? That's the reason I dared to try it.
So in this sheaf of local differential operators, is it a great vector bundle or not?
I don't think so. But I have no idea. I have no counterexamples, right? But I really don't think so. I think there is no reason why this should be locally finitely generated. It will be probably finitely generated, because you can choose some because you can always choose some generators maybe of your modules of your spaces of sections, and then but freely I personally don't think so. I think the answer is no. right? Because I will show you the notion of differential operators for each k, and this k goes for infinitely to infinite, right? And all of these bundles, I will tell you, would have to be sub-bundles of this. I think, maybe. Right? So just waving hands. So if this would be graded vector bundle which has finite total rank, it would have to contain this ever-growing subsheaf of differential operators, because is it growing all the time? I think yes. I think it does. Definitely it does. But really, I have no reason to believe that this is a graded vector bundle. But what is a graded bundle is an example of. So this is definition. So I want to tell you what is a. Sorry, I won't. There's another example, which I should have said like here. So it's part of this sub-example of this example. To give you an example of C infinity and mu linear map, so to any function, I can assign a mapping from gamma EU to gamma EU, which is denoted as lambda gamma UE gamma gamma EU, and I declare it to be the left translation. So lambda f acting on psi is just f times psi, and this is C infinity m u linear. Okay, so gamma f is lambda f, sorry, is C infinity m u linear of degree f. Degree. I'm struggling with basic English, sorry. This is easy to check. If you take here g times psi, then it appears here, and you have to take it out. And because it's graded cumulative, you pay exactly the sign -1 to degree f times degree of g, which is exactly this sign here. So this is example. So this is called left translation. Left translation. And this left translation is vital for the following definition. So I will hide it. And it's vital for the definition of differential operators. So I take U to be some open subset of M. E is graded vector bundle. And where it is? Somewhere else. Okay. And I will fix some non-negative integer. Okay. And I say that graded R linear map. So I'm talking about graded operators, linear operators. R linear map D, which goes from gamma EU to gamma EU, is called a K order differential operator on E over U. So it's called K order. You have to be careful with using the word degree. So K, not K degree differential, but K order differential operator. If. So if K happens to be 0, you are not surprised that I assume that if K is 0, then it has to be C infinity M U linear. C infinity M U linear. So degree, no, 0 order differential operators are just C infinity M U linear maps. And if K happens to be greater than 0, then you simply say that the commutator, graded commutator of this D with this left translation operator is k minus 1 th order this operator, differential operator on E over U, and this has to be true for all functions. So this is kind of inductive definition, so if you want to arrive to degree 7 differential operators, then you start from 0, inductively build the spaces, and you end up with 7th order. Of course, I have like 5 minutes, exactly fine. So, of course, you can write it straight away definition. And this is a graded commutator. So D has some degree, lambda f has some degree. So this is D composed with lambda f minus 1 to degree of D, degree of f, lambda f composed with D. And I will now introduce a notation which you will forget next time. So you take any G where any G in N. So we take any positive integer and then construct kind of iterated and every J couple of functions in U, in N over U, and then you can define this, like this, J, but it's just nested graded commutator. So I come with D with lambda f1, then I come with this guy with lambda f2, and then so this is just the nested graded commutator, nothing else. So the definition tells you that if you so depending on the number J, it's k minus jth order differential operator if D happens to be kth order differential operator. But this is well defined for any graded linear map, so this isn't really exclusive to differential operators. And then you can of course say, just remark, that D is, and I forgot to tell you how I will write the graded vector space of differential operator of kth order. This is denoted like this. So this is the graded space of differential kth order differential operators on E over U, and this is true if and only if, right? If this, you can show that if you plug k plus 1 functions into it, and this is 0. Because if you plug k of them, it will be C infinity mu linear, and this C infinity mu linearity can be written as graded commutator with another lambda fk plus 1. So you can directly tell that k for the differential operator satisfies for all functions, of course. Okay. So this is my definition. Then there are first 2 observations. There are actually 3 observations, and I will stop there. So first of all, and they are very easily proven. That's good thing. So first of all, differential operators are local. So if k a u is a subset of log e mu, so every kth order differential operator is a local operator, which means then you can restrict them. That's the first thing you want. And in fact, you can prove, and it's also very easy, which is interesting, that you can then use restrictions from here, right? You can define the restriction of differential operator to be restriction of the local operator, and it happens to be again differential. So you have to prove, but that's true. So basically, what I'm saying now, that this Ek can be viewed as a subsheaf of this sheaf. So this is a subsheaf or sheaf of, and also you can prove that it's a submodule. So it's a subsheaf of C infinite M submodules of this sheaf. So it's sheaf. It's a consequence. Subsheaf means that it's a sheaf. So it itself is a sheaf. So differential operators of kth order form a sheaf, which happens to be subsheaf of this sheaf of local operators. And the proof is kind of nice, and it uses induction on K, of course. So you start from K0, and you prove that this is true for linear C infinite mu linear operators, which is you use some bump functions to do that. I don't think so. Maybe not even. Maybe it's not even true. Maybe you can just prove it somehow directly, and then you inductively prove that if this is true, then you basically use this description to prove that this is local, blah blah blah. So you can. It's kind of nice exercise. And the first observation, of course, which is trivial, is that this canonical inclusion, because every kth order differential operator is also automatically k plus 1 order differential operators, and all the other higher things. That's clear from this description example. If you commute it with one more lambda, doesn't change this condition. So it's obviously true. Okay. So at this point, I will finish. And just a disclaimer, of course, this definition is this is very easy description of differential operators, because you can prove immediately all these kind of complicated statements. But it's not anyhow clear why this should be called differential operators, right? Why I would call these differential operators. That's the first thing. And the second thing, does it form a sheaf of section of some graded vector bundle? And the answer to both those questions, first one is that if you write it locally, it really contains some partial derivatives of components of sections you are acting on. So up to the order k. So this explains the name, k for the differential operators. And the second answer to the second question is yes. So it's really, and it's proved at once by looking how it looks locally. So you can locally take this operator and locally expand it as some finite sum of operators which acts somehow well described using local coordinates, and then you can prove that this description is unique, and that's it. So this proves this thing. And then I will tell you next time, maybe if there is time, there is a well-defined notion of a symbol, principal symbol of differential operators. So everything works as expected. You can from it extract, say, for example, Atiyali algebroid of graded vector bundle. And then I will hopefully tell you about graded jet bundles, which is a bit more interesting, because this is straightforward and everything works as expected. For graded jet bundles, everything almost works as expected, but you have to do some gymnastics with some operations with pre-sheaves, because what does fail, and it is not clear how to do, of course, in standard geometry, graded jet bundle is defined using its fibers. So you look at the fiber at the point, and you define what is graded jet space over this point. So these are just equivalent classes of sections which such that their derivatives to order k agree at the point, something like that. And this doesn't work here at all, right? Because evaluating some section or its derivatives at point, you lose almost everything about this section, because you throw out everything which has non-zero degree away. So you lose a lot of information and you get nothing sensible out of this approach. So you have to really work directly with the sheaves of sections. So I really produce a sheaf of sections of this graded chess bundle directly, starting from sections of E. And that's what the construction is. And it probably works. No one objected yet. And you won't either next time, right? Okay. Okay, thank you.
Time for some questions.
Maybe a naive one. So basically from part 3, you know that you have this inclusion, and then for part 2, you know that if A always is always the subsheaf of local. So if you take a limit or something like that, what will be the difference?
Yes, that's of course, I expect this question. Of course, people who actually do geometry are always interested in this infinite chat. Whether it exists, I don't know. I have not thought this far. I will probably have to, one moment, right? To produce, I would have to produce some. It's something. I think it's because when people work with modules, they do some projected limit or something like that, which I don't know how to do here. Maybe you can somewhat directly define what it is, but I don't know.
Yeah, so maybe it's related to Ramadas. I didn't quite hear, but basically, so what would be a concrete simple example of a local operator which is not a differential operator?
Local operator which is not a differential operator, that's another good question, which I also expected, and unfortunately I have no idea. So that's it's maybe true that I don't know.
So in ordinary case, do you have an example?
I'm not sure. There is theorem that reacts here in its most setting, which characterizes differential operators in terms of what happens.
Exactly. Yeah.
So, but maybe in the graded setting, we can form something like an infinite sum of differential operators of increasing orders. I didn't relate it to Ramadas. And then you can hook up an operator which is like a formal differential operator of infinite order, which is not.
But yeah, maybe there is a. Yeah, I would have. So you are claiming that for ordinary case there is a theorem saying that every operator which is local in this sense is differential. So I can try to, maybe it works. I'm not claiming it doesn't. I don't know.
So you have 2 weeks time.
I have 2 weeks time, yes. So I have 2 weeks time to work out infinite chess bundles and. Of course, I will try.
I have a question about the beginning of the talk. So, as I understand, one of the regular sources of graded manifold will be the following construction. You have a regular manifold, you have a vector bundle over it, let's make it graded in new sense, and then I build graded exterior algebra.
Yeah.
And it will give me a desired sheaf function.
This works, yes.
So, and in several cases there is a theorem that if you work in a smooth category, then all your manifolds are this type. And if it's an analytical category, then you have a non-split type. So, is there something that
there are results of this type here. I don't know if there is a result for this particular definition I use. I'm not completely sure, but there are others who prove such statements. And for example, Kotov and who are the other guys there? I don't remember. Sannikov and Konsin, I think. Sorry, pardon my French. And they do something similar, and they define them slightly differently, but they should be equivalent, and they prove something like it's called Vysoký theorem for supermanifolds, right? And there are many versions of this Vysoký theorem for graded manifolds of various types, because there are many different definitions of graded manifolds, unfortunately, so which are not completely equivalent. So there are different definitions. Then I use one which I wrote in my paper on graded manifolds, which is the best one, of course. But there are others. For example, Z-graded manifolds can be defined as supermanifolds with some grading vector field such that eigenspaces of this gradient vector fields are degree eigenvalue functions, right? And there are some versions of Bachelor theorem for this kind of supermanifold gradient manifolds also, and there are some versions of it. But definitely, it will be. It's a nice result, but in a sense, it's nice. But I want to keep because it's highly non-canonical usually. This Bachelor theorem is not. You have this choice of vector bundle you use, or sequence of vector bundles or whatever. It's not canonical, so you know that it exists, but it's not really. It doesn't tell you too much about the actual gradient manifold. You can use it in some proofs, for example, of course, but yeah. But there is something like it for gradient manifolds, definitely. Yes. And it's important to have these theorems, of course.
So any other question? Maybe I would have not very sure it will be question, but as you mentioned how you can describe those intelligent jet bundles and relate to the question whether there's only differential operators being those C infinite linear. Does it make sense to find the relationship between how you can compute stalks and relate them to fibers of your infinite chain bundles? Or did you
no idea
think about this?
No.
Yeah. Okay. Maybe it's an accurate question. Okay. So
I have no idea. Simple as that.
yeah. So if there's no other question,
No, nothing from online. No.
So then, thank you again for a nice lecture.
Thank you. I'm intentionally saying not the last part, next part.